Welcome back to ECE 442-542. In this video, what we want to do is try to illustrate by example what we're dealing with when we're looking at root locus rule number 5, which we were associating with the departure angles and the arrival angles of complex poles and complex zeros. Let's just get started with a particular example. In this case, hopefully it's clear that we have a real zero at 1/2 and a complex pole pair in the denominator, or poles that are complex conjugates of one another, at 1 plus and minus j 1/2. If we sketch that in the z-plane, we now have our 0 at 1/2, and we have poles at 1 plus and minus j 1/2, where these tick marks are now at every 0.5. And what we would like to do is figure out, what does the root locus look like? First, we can say, how many branches do we have? Well, we only have 2 poles, so we're going to have 2 branches of the root locus. We know the root loci, or the branches of the root locus, start on the poles and end on the zeros. Those zeros could be either finite zeros or infinite zeros. In this case, we have 2 poles and 1 finite zero, so their difference, 2 minus 1, we have 1 infinite zero. We have then an asymptote angle of 180 degrees divided by that pole zero excess, or 180 divided by 1. So we are now having an asymptote that's going off at 180 degrees or minus 180 degrees. We also can use rule number 2 to determine that, in fact, the left side of that real axis to the left of the 0 at z equal to 1/2 belongs to the root locus, and we should have 2 branches on that particular line segment. What we want to know with rule number 5 is, how do these branches depart from the poles? And that's really what rule number 5 is. We could compute the reentry location along that segment of the real axis that belongs to the root locus to determine where they come in, or where those 2 branches return back to the real line. But for rule number 5, which is the departure angle, we are now wondering, do they depart straight up, which would mean that we would have a departure angle of 90 degrees, or do they do something else? Do I'm meaning the 2 angles and their mirror images of each other, is that departure angle, alpha sub d, bigger than 90 degrees? And if it is, this indicates the angle immediately after sort of leaving the pole that the branch makes with that positive real line segment, and we would have its mirror image down here. We want to know, how does that depart and then come back in to the real line and produce some root locus that might look like what I've just sketched. And the way that we can find that is, in fact, by using the phase angle condition and examining a point very close to one of those complex poles. Let's choose this one just for consistency. We'll choose the complex pole that's in the upper half of the z-plane. If that dot that I've now indicated, we can see then that that dot does make an angle with this positive real line segment to the right of that pole. But if that dot is an epsilon distance away from that pole, we effectively then can just use that pole location to determine all the other angles from our poles and zeros. Our plants poles and zeros, and if we had controller poles and zeros, those would also be in there. But if we now indicated desired closed loop poles at these triangles, we would not use the angles from those triangle locations to the pole in question, and that's a common mistake that students make. Here we really only have 3 angles that we're working with. Let me call this lower angle theta sub p sub 2. This upper pole angle we're calling alpha sub d for its angle, just to make sure that we know that that's the angle of departure. And here is the angle from our finite 0 up to that pole in question. And now from the phase angle condition, we now know that the angle of G of Z, in order for the points Z to belong to the root locus or to be anywhere on that red pattern in the Z-plane, the points have to have an angle of minus 180 degrees. Using this angle of G equaling minus 180 allows us to actually solve for alpha sub D. The angle of G is now going to be the angle of that 0 factor minus the angles due to the poles. In this case, we have the pole in the upper half of the complex plane, and we have the pole in the lower complex plane, and we're interested in their angles, or in this case, those now need to sum to minus 180 degrees. If that point Z is or belongs to the root locus. So in this case, the angle of the 0 factor, the 0 factor is this factor Z minus 1/2, we now have labeled that as an angle theta sub Z minus the angle due to the upper pole, and again, this angle is with respect to this point that's just a very small distance away, but it still has an angle relative to this positive real line extended to the right of that pole. We could still measure that angle. That angle we were calling alpha sub D for the departure angle, plus the angle of the pole that was the conjugate of the pole that we're measuring with respect to. And those now need to equal minus 180 degrees. By inspection of this particular plot, or it's pretty easy because the poles are at 1 plus and minus j1/2, and the 0 is at 1/2. So this theta sub z is, if it was drawn accurately, would have an angle that has an opposite side of 1/2 in length and an adjacent side of 1/2 in length, or an angle of 45 degrees. We now have then 45 degrees minus alpha sub d plus theta p sub 2. This angle, it's looking straight up to that pole, is 90 degrees. And those have to sum to minus 180. We now have algebraically 45 degrees minus alpha sub d. I need to make sure, and I just emphasized algebraic, that's minus 90 degrees is equal to minus 180 degrees. We now have then alpha sub d equaling 180 degrees minus 45 degrees, or alpha sub d is equal to 135 degrees. That now tells us that we are actually departing from that pole right here. If this was our pole in the upper half plane, we are now departing that at an angle of 45 degrees up from the negative real axis, or 45 degrees beyond 90 degrees. So we're now departing that pole at an angle of 135 degrees. This particular departure angle is 135 degrees. That's really rule number 5. If we wanted to now think about design considerations or different pieces of this particular problem, maybe somebody's now interested in stability. Now we are wanting to know, when does that root locus enter the unit circle for the first time, and both branches stay inside for a given value of k. And now it is somewhat helpful to have sketched this a little bit more accurately so that your angle of departure of 135 puts you at a better understanding of where that now is entering the unit circle. So if we now said that we wanted to be at this location, and I'm not sure that that location is accurate because my particular departure angle is not really 135, it's more like 110. But just use your imagination. Now we want to know, how much do we crank up the gain k to get to that cloud location? And we could find that with a little trigonometry. We know this distance is really a radial distance because we actually have 2 poles and a 0, and if we envision those 2 poles rotating to be real, they would stay that same radial distance away. So if we said that this is now at some r distance away from the 0, we now can figure out what that r is because we know the location of the 0 and we know that location of the pole. So now let's just say that we are, for demonstrating what we can now do based on the tools that we possess, let's now examine how to find r. In our case, if we look at this, if we said that z, this particular distance is z, and this now is at, let's say, p sub 1, now that we know that z plus this vector r at a given angle, which the angle is theta sub z, is now going to give rise to being on top of that pole of p1. So now, using some vector addition, we can now say that z plus r e to the j theta sub z should equal p sub 1. Or r e to the j theta sub z is equal to p sub 1 minus z. And if we take the magnitude of both sides, we actually know that the angle of a product is the sum of the angles. And from Euler, we know that e to the j theta, which you could rewrite as cosine theta z plus j sine theta z, has a magnitude of 1, and that now disappears. And now we can find actually the length of that radius from the 0 to the pole, and that's now just the difference between P1 and Z, but P1 we said was at 1 plus J1 half, and Z was at minus 1 half. This isn't too challenging to do the algebra. Now we have 1 half plus J1 half. We now have equal distance of 1 half horizontally, 1 half vertically in our rectangular coordinates. We can now find the hypotenuse of that, and that's now a right triangle, and so we really know that this is the square root of 2 times 1 half in terms of magnitude, or the radius now is the square root of 2 over 2, or 0.707. And that now allows us to think about what we might want to be interested in, which is if we now have these poles and we have a 0, we are interested in where does that root locus come back into the unit circle, and we've just computed this is R, so this is also R. This distance, because this cloud is on the unit circle, that has a value of 1, and this distance hasn't changed. That's still Z is equal to 1 half, and now we know that this R is, let's say, equal to A, which is the square root of 2 over 2. And if we wanted to compute this angle, we can do that now by the law of cosines. In this particular angle, let's call it theta sub d, because that's the angle of our z value in this case. We can now write the law of cosines to find theta sub d, or it's now, if we called this particular value in our law of cosines b, and let's say that this radial distance of our unit circle is c, and I've already called the r a, now we can say that we have c squared plus b squared minus 2bc cosine of the angle of opposite, or the angle associated with side A, which A is opposite the angle A, so that's cosine of theta sub d, is equal to A squared. We know C, that was 1. B, we know, is 1 half. And A, we just computed to be this square root of 2 over 2. Plugging in all of those numbers and solving for theta sub d, we can compute theta sub d as the inverse cosine of 3 over 4, which ends up being 41.41 degrees. And now we have that this z cloud, or the point where we just enter into the unit circle on our root locus, is now going to be r e to the j theta sub d. Our r was the square root of 2 over 2, and our theta sub d was this 41.41 degrees, and that's now just some x bar plus some jy bar, and if you go through that, you end up with this being roughly 0.75 plus j 0.661. And we could then calculate the gain k at that point, and doing that, we would then find that this particular gain value is 0.25, and so we need to crank up the gain on our root locus to be at least 0.25 in order to become stable. And we sketch that root locus here. And now this particular cloud says, oh, the gain k to get us to that point needs to be 0.25. And once we get there, then we're at the lower limit of k for stability. And then we could determine what is the gain to get us to leave the unit circle, or the gain k at -1. Where again, doing all of that, we actually have z minus 1 minus j1 half, z minus 1 plus j1 half, all over, for this particular example, 2 times z minus 1 half, and we evaluate that at z equal to -1. You plug in all of those numbers, and you end up with 1.42. So that's now the maximum value of gain k for stability. And k in this case would then need to exceed at least 0.25 to get to the cloud, and then it needs to be less than 1.42 to remain inside the unit circle. And this is our, let's say, range of k for stability. In fact, before I started this, I went ahead and performed a little MATLAB. I input that transfer function with the TF function in MATLAB. I now have my 2 times the 0 factor all over the denominator factor written as a polynomial. And in this particular case, I didn't specify t, our sample period, is unspecified. And that's actually what MATLAB tells us when we use that -1 for the sample period, capital T. Then I went ahead and simply, MATLAB does all of this sketching for us very quickly with just one command. We just say our locus of the transfer function. Let me slide down, and now you can see that, oh, in fact, we were pretty accurate with our, or in terms of our generic shape, we were pretty good with how we had sketched the root locus. And now what I've done is I've actually issued one more command after the root locus command to pick off, or to select a point in the graphics window. This rLocus find allows me now crosshairs to be superimposed on the root locus diagram, and then I can left mouse click wherever I locate those crosshairs. And in this particular case, I located those crosshairs where before we were intersecting with the unit circle for the first time. And in fact, this is what we were calling our Z cloud, and here is the gain at Z cloud. Then I went ahead and clicked on a different location of crosshairs, and in fact, in this case, if we look at what happens at -0.2 on our root locus, here is now -0.2 in the z-plane, and this is in fact the re-entry point. And if we look at that corresponding to -0.2, we can see now that the gain at re-entry is now 1.2. And that's less than what we calculated as the upper limit on stability for K, which is a good thing. And that's what I did with my last crosshaired rLocus find choice, I tried to now locate the crosshairs near z equal to -1. So I'm at now minus 0.9988 or 0.999, which is roughly -1. And here is now our gain, k, at -1, 1.42, which is really what we'd calculated before. So this is exiting the unit circle. I did one more thing. I went ahead and I said, let me now try to find on my root locus some points that I might like to have for closed loop behavior. And I'll call that now my triangle location. I now located my crosshairs with the rloc find command to be at that triangle location. Here's now z triangle. It's at 0.25 plus and minus j 0.67. It's just the 1 point, so it's the plus 0.67. The gain at that value is now 0.74, and I can use that gain here to scale my transfer function g of the open loop plant to generate, using the feedback command, a closed loop transfer function with just a gain controller. Here's my closed loop transfer function. I went ahead and calculated the poles of that closed loop transfer function, and in fact they are what I hoped they would be. And then I introduced a new figure window. I issued a step command, and that's now my last plot, the step command. And I looked at the peak response, and it looks like I have an overshoot of 100%, which is pretty high. I have a settling time of 13 sample periods, and my final value as at 0.75. And I can find all of these characteristics by, inside MATLAB, I simply do a right mouse click, and that now allows me to open up this option to look at different properties of this step command. And I just said, let's look at the peak behavior, let's look at the settling time, and let's look at the steady state, and that's now what resulted. We have 100% overshoot, a settling time of 13 samples, and a final value of 0.75. If that's not acceptable, then we either need to relocate these triangles by a different choice of gain k, or we may want to introduce a different controller. In this case, all we did was have a gain controller, and the main reason we did that is so that we could then see how to calculate the departure angle from these particular complex poles. And in fact, it is verifying that the departure angle, as long as our axes are equal in terms of horizontal length is equal to vertical length, then we'll have an angle of 135 degrees. And that's what we wanted to demonstrate in this video.